So we're looking at complex numbers, and we saw that when we were trying to graph a parabola who didn't have any x-intercepts, its x-intercepts actually resulted in complex numbers, and that happened when using the quadratic formula or completing the square. So this parabola has x-intercepts in an imaginary location, clearly, because they don't seem to exist, so they must be imaginary. Let's take a look at some set of coordinates. Let's say we had 3, comma 4i. And I want to plot that in the Cartesian coordinate plane. Alright? I'd want to go over 3. Alright, so somewhere here should be some point. But there isn't, because this is a real number line, and only numbers on this line are real numbers. There's every spot on this line will qualify as a real number. So if I pick this spot, that is a 3/8. This is a 2.359869, some sort of irrational number. So there's no space in the real Cartesian coordinate plane for imaginary numbers. They actually cannot be graphed. They can't be graphed in the real number plane. Alright, in what we call this is R2, meaning a two-dimensional real number space. Whereas a number line would be R1, space, meaning 3 dimensions, would be R3. Alright, so this would be the real line, the plane, and space. So complex numbers cannot be graphed on any of these. They can be graphed on their own plane. This is called the complex plane, which has 2 different axes. It has what's called the real axis and the imaginary axis. And here's what's interesting about the complex plane. Alright, so this would be, there's a symbol for this, for complex. I believe the symbol for complex is this. Just like this is the real number line, this is the complex plane. So this is the complex plane. And if we wanted to graph a number like 3, they're not coordinates. You have numbers in this form, where a and b are real numbers. You can actually graph real numbers and imaginary numbers on the complex plane. So if you had to graph the number 3, that would be located here. Let's actually do that in blue. So if we wanted to graph 3, that would be located here, where the value of the real part is 3 and the imaginary part is 0. If we wanted to graph 5i, that would be located up here, where the real part of this number is 0 and the imaginary part is 5. If we were asked to graph, let's say, -3 minus 4i, that would be located this way. 3 in the real direction and negative 4 in the I direction. Alright, so numbers can be graphed in the complex plane. Real numbers and imaginary numbers. So this plane actually accounts for all numbers: imaginary, rational, irrational, integers, whole numbers, counting numbers, and so on. So what are some uses of the complex plane? One is finding the absolute value of all numbers. So the absolute value of 3 is its distance from the center of the origin of the complex plane, which is a distance of 3. The absolute value of radical 5, so this is the absolute value of, the absolute value of 3 is equal to 3, but you knew that already. Yeah, so the absolute value of 3 is equal to 3. The absolute value of 5i is equal to 5, because the distance from 0 is 5. And that brings us to an actual more interesting example. What is the distance for a complex number? Well, to do that we'd have to take its we'd have to find its measurement using the Pythagorean theorem. So it's 3 in this direction and 4 in that direction. So in this case, the absolute value of negative 3 minus 4i should be equal to 5. Alright, because that's 3 squared plus 4 squared is equal to c squared. So that's 9 plus 16 equals c squared. So 25 is equal to c squared. So c is equal to 5. Alright. So let's try one more example. So I'm going to be moving back here until I clear the grid. Alright, so let's make up some other complex number. So let's say we had, I don't know, it doesn't matter. 5 minus 12i. Alright, so on our grid, it's going to put us 5 over this way and 12 down. So to find the, if we were asked to find the absolute value of that, we would be looking for the distance of this line. So making our right triangle, this distance is 5, this is 12, and 5 squared plus 12 squared is equal to c squared. So we got 25 plus 144 equal to c squared. So 169 is equal to c squared, which makes c equal to 13. So the absolute value of 5 minus 12i is equal to 13. Alright, so let's try one more example. I was trying to get one with a radical, but I didn't realize what I was doing. So let's try that again. So some non-Pythagorean triple should be a good choice. So the absolute value of, I don't know, 6 plus 4i. Alright, so we go over 6 this way, 4 this way. We have a right triangle whose measurements are 6 by 4. So we're trying to find c again. So we get 4 squared plus 6 squared is equal to c squared. So 16 plus 36 equals c squared. So that's 52 is equal to c squared. So the square root of both sides will be, so radical 52 is equal to c. This simplifies to be 4 times 13. So that's 2 radical 13. So the absolute value of 6 plus 4i is equal to 2 radical 13.